This video will explore the difference between velocity and speed. Average speed is the distance traveled divided by the time required to cover that distance. Recall that distance is a scalar quantity and it is defined as the total path length covered by an object, regardless of the direction. So the question, how far does a jogger run in 1.5 hours if his average speed is 2.2 meters per second? Well, recall speed equals distance divided by time. If we're looking for distance traveled, we solve for distance and we get distance equals speed times time. And so we multiply 5,400 seconds by 2.22 meters per second. Our seconds cancel, and I'm left with about close to 12,000 meters, or about 12 kilometers. Contrast that to average velocity, which is the displacement divided by the elapsed time. Recall that displacement is a vector that describes the difference between a starting point and an ending point for an object. Displacement, or change in position, is often written as delta x. So we could ask the same question about the jogger running 2.2 meters per second for 5,400 seconds, but we'd have to know a bit more to understand his average velocity. The reason being, he might be running from home to a destination or from that destination to home, in which case his average velocities would be associated with opposite displacements, positive or negative. So with velocity, we need to understand direction, and we need to understand starting and ending points only. So we could ask the question, is your average velocity for a typical day 0? A concrete example of this is the world's fastest jet engine car. In order to set land speed records, you must travel down a track one direction and then in the other direction. Your average velocity is calculated for each direction. Notice your average velocity on the way out, 1,609 meters in a certain amount of time, is positive. On the way back, it's negative. If we want to know, did you set the land speed record, we could average those as speeds, 339.5 and 342.7 meters per second. Because in each case, the average speed would just be positive 1,609 divided by each of the times. But if we're asking about velocity, we need to understand direction. Again, we could ask a similar question to the previous one. What was the average velocity for the full lap? The answer to that would be 0 meters per second, because he began in the same spot that he ended. So if we want to look at the graphical piece for this, we could look at object A's position versus time graph. Object A seems to pick up 1 unit of position for every unit of time. Well, if we recall that velocity is displacement over time, we could calculate velocities for each time segment. For instance, in the first second, the object travels 1 meter in the positive direction for a displacement of +1, and it travels at +1 meters in 1 second of time for a velocity of 1 meter per second. Now in the second second, it does the same. It travels 1 more meter in 1 more second for an average velocity of 1 meter per second. So if we want a graph of velocity versus time graph, we look at those individual velocities that we've calculated and we plot them. And so we know for each moment in time, even if we take a half a second, we know the object will go half a meter in half a second for a velocity of 1 meter per second. So what we're doing is we're plotting those 1 meter per second points that we've calculated, and if we connect those points, we get a flat line that suggests our velocity is constant at 1 meter per second. What do you think the velocity versus time graph would look like for object B? We could look at the second position versus time graph, which is a little bit more complex in that the object starts out seemingly moving very quickly. It's moving in such a way that it travels 1 meter in the positive direction in only 1/2 of a second, or velocity of about 2 meters per second. In the next half second, it only travels 1/2 a meter. And so if we're looking at the average velocity for that segment, it's about 1 meter per second. In the next second, it seems to travel even a little bit less than that. And in this region, around 2 seconds, it appears that the object isn't actually gaining or losing any position, though it's taking time to do that. We would call that not moving. So if we start to plot these velocities, we start out with a fairly large velocity. We drop our velocity, and in about 2 seconds, we know we're not moving at all. And when the object reaches that peak in its position versus time graph, what does it start doing? It starts to lose position. Its displacement becomes negative every second, and it's going to look completely symmetric for the first half of the graph, except everything's going to be negated. So if we're plotting those velocities, what we see is those velocities drop into my negative region, because we're just plotting the values of those displacements divided by time. So my velocity versus time graph looks like that. So lastly, if we want to do some calculations and connect the graphs to the algebra that we saw in the beginning of this video, we could find the total distance traveled. Remember, this is the path length. So the object goes from 0 meters, it picks up a meter, and it picks up another meter, it loses 1 meter, and then it loses a second meter. So it picks up 2 meters on the way out, and then it loses those 2 meters, so it's traveled a total distance of 4 meters. If we want to calculate the average speed, all we need to know is how much time that took. It appeared to take 4 seconds. So 4 meters divided by 4 seconds is 1 meter per second average speed. The total displacement just depends on where it ended and where it began. The displacement is therefore 0 meters where it ended minus 0 meters where it began for a 0 meter displacement. If we want to calculate the average velocity, we just need to divide that by the 4 seconds of time. 0 meter per second average velocity, 0 meter total displacement. We could calculate that from the velocity graph, but that'll be an exercise for later.